Hi everyone, welcome to the third and final EECS 280 Project 5 video. This video will focus on the actual driver used in the project. There will be two main parts to this video. First, we'll look at an overview of what machine learning is and the problem that we're trying to solve with it here. Then we'll look at the specifics of how our Project 5 machine learning classifier works. First, we should understand what we're trying to do with this program, which is to solve the classification problem. We need to figure out for some given input, what category does that input belong to. We're going to first look at how a human might solve this problem and then use that to inform how a computer can solve this problem. Here we have our classifier. Oops, that's our classifier. This can be thought of as one big function, which is executed by the human brain or a computer program. It's conceptually the same. It would basically get some input and then turn that into some output. Here we have an example input, which is an image of a cute dog. If we provide this image to a certain classifier, it can tell us with some degree of certainty that this is an image of a dog, as opposed to an image of a cat, an image of a horse, etc. And inputs are not just limited to images. We can use text, audio, and other formats, depending on the classifier. Here we'll look at an example that's relevant to Project 5, which is a sentence from an EECS 280 Piazza post. Our classifier can tell us that this input probably belongs to the Euchre category. This is basically what you'll be doing in this project. Now let's break down this classification process further. One way to think about how a human might classify this input is to identify features from the input and raise or lower the probability that a given category is the correct one. The amount by which we raise or lower these guesses is based on how common those features are for other inputs of the category. For example, we can look at this sentence here. Some of these words like which, is, the, or, these are pretty generic words. They could occur in inputs belonging to any category, and they're not very specific. So they don't tell us much about the input, and they're probably not going to change our probabilities much. But you might notice that there are other words which can tell us a lot more. Words like bower and card are probably seen very often in posts labeled Euchre, and very rarely in other posts. There are also words which might be somewhere in the middle. Greater could be talking about comparison of two cards, or maybe two nodes in a BST. Left and right can also refer to left and right bowers, or children of a tree node. So words can range from pretty evenly distributed among all categories to very specific to a single category. And as I go through each word in this post, I build up this set of probabilities over here for each category that I know exists. These probabilities are refined as I read through more of the post. Eventually, I've finished reading in the post, and I'm left with my final guesses as to how likely each category is. In the end, I pick the category which this input is most likely to belong to and select that as my final decision. So as I give this sentence here on the left to my classifier, I get these probabilities out, and I say, okay, Euchre is the most likely of all these labels to be the correct label for the sentence. So I will use that as the output for my program. Just like how humans aren't born knowing the difference between a dog and a cat, machines are not built knowing the difference between P3 Euchre and P4 Web. We could hard code all the inputs that lead to a certain category, but this quickly becomes way too large of a task to handle as the complexity of a problem increases. So instead, we look again to how humans learn to classify things, which is to notice similarities to previous examples that we've seen before. Humans learn by drawing on these past experiences and information to make decisions about newly presented input. Similarly, we can build computer programs which use knowledge gained in the past to make decisions about new input. Simple machine learning networks generally work in two distinct phases: a training stage where the classifier learns about the problem, and a testing phase where the classifier is used to make decisions. You can notice that there's a pretty discrete boundary here. Here on the left is training, and there's a pretty solid boundary between that and testing. There's not a lot of overlap, at least in our applications. In the training phase, we give the classifier some pre-classified data to learn from. It analyzes these inputs as well as the category they belong to and begins to understand what sort of inputs lead to or don't lead to a given category. Then in the testing phase, we use this now trained classifier here to categorize some second set of data. The classifier uses the information it learned in the previous stage to select a category for each item in the testing data. The key insight here is that this testing data contains new items which the classifier has never seen before, but each of these items must have similarities to those seen in the training data set. Most of the time, this means they come from the same data source or same kind of data source. In the end, we do the same process that we discussed before, where we pick the most likely of the categories that we know of and classify our testing output with this category. Let's take a look at an example of what this training and testing process looks like in Project 5. Here's an example of some training data from the starter files. This is from a file called train small.csv. Here we can see several different training inputs, which are the posts, the Piazza posts, as well as the category they belong to. The classifier will study each post and the label it belongs to build up knowledge of what kinds of inputs contribute to which categories. And as an aside, in this project, we use what's called the bag of words model, meaning that repeat occurrences of a word in an input don't do anything. So you only need to worry about the unique words in a post. This second the here in this post, it doesn't do anything else to the input. Anyway, this here is a post from test small.csv. Notice that this post has never been seen by the classifier before, right? This blue bubble here that represents the trained classifier is the same as this one, right? And the classifier has never seen this exact string of words before. But it has seen several different training inputs from the same data source, which is the EECS Piazza, and it studied what made each category different. For example, we saw a post in the training data that used the word dealer. I believe it's right here. So that implies a very high probability that this post belongs to the euchre category, right? Because we can see the word dealer here. And so we look to the classifier, which tells us that in our training data, we saw posts with the euchre label that had the word dealer in it, and we didn't see posts in other categories with that label, right? The one post we see here from calculator doesn't include the word dealer. So that implies a very high probability that this post belongs to the euchre category, just based off this one word. So we repeat this process with all the words in the testing post to get some final probabilities for this testing post. And again, we select the maximum of these, which in this case is probably going to be euchre, and we declare that as kind of our guess or our prediction for this one post. And for every post in the testing data set, we'll repeat this process, and each of those posts will have a similar classification. As an aside, there are certainly limitations to this learning process, both for machines and humans. In our classification problem, we can't predict the probabilities of categories we haven't trained on. A human wouldn't be able to categorize images of animals they've never seen before because they don't know what categories these animals could belong to or what the key features of these unfamiliar animal categories would be. Similarly, if we train our Piazza classifier on EECS-280 posts, it would fail to predict labels for EECS-281 Piazza posts in the testing phase because it doesn't even know what these categories for the EECS-281 projects are. It would basically be classifying these EECS-281 posts under EECS-280 categories. And this shows the importance of having training data and testing data from the same source. We can also be led astray by our training input. When learning English, toddlers may incorrectly learn grammatical rules. If a toddler knows that the past tense of walk is walked, they might incorrectly guess that the past tense of catch is catched instead of caught. This explains why even when our training and testing data come from the same source, we can get inaccurate results and can't predict every testing post, or I guess every testing input correctly. And although larger training data sets and more complex models can improve our prediction accuracy, testing inputs that don't follow previously observed rules very closely can be difficult to classify. This isn't super pertinent to Project 5, but I guess it can explain some of the results you might see as to why you're not like perfectly predicting some outputs, or why you can't just use this with any type of CSV. Now that we understand how classification works, we can plan out how we want to structure our classifier program. This program should first train itself on a dataset of Piazza posts, then predict a label for each post in the second testing dataset. As long as you follow the spec, the implementation of the classifier is up to you. But a good starting place is looking at the different steps our program needs to accomplish. We'll first need to get our data from the command line like we did in projects 2 through 4. Then we'll use a singular instance of an ADT to manage our program's data, like we did in project 3 and the web portion of project 4 if you did that. Then we'll run the 2 steps that we discussed in the previous slides. We'll train our classifier on one dataset, then use this trained classifier to classify a second dataset. These are two distinct phases. Can you see how each of them can be encapsulated into its own function? Here is everything the spec says about training our classifier. You'll notice that there's not much here at all. This is because the training process is relatively simple. For each post in the specified training dataset, you'll analyze the text and record some information which is listed here. Note that you should read in each training post, then modify all your data structures at once. Your program will be too slow if you iterate over the training set multiple times. Some information will be updated on a per post basis, and some may be updated based on each word in a post. So be thoughtful about how you use and nest loops in this part. And this part of the project is where we incorporate the map data structures we've learned about previously. In general, we use a map as a set of key value pairs, and then we don't worry about the implementation beyond that. And as a matter of fact, you should import the standard library map instead of your own, as your map will be too slow for the larger data sets we use. For each of these pieces of information, you need to figure out what C++ type can be used to keep track of it. The first two items are both number of something. So that can be an int, which is not that complicated, I don't think, and you'll update it depending on what the data you're reading in looks like. So sometimes you might increment it, sometimes you might not increment it depending on what you're looking at, right? Then for the remaining three items, you'll ask yourself if you're able to interpret that information as a key value pair. If so, you can probably use a map. So when I look at this third item, I notice this for each phrase. That means for each key, I have some corresponding value. Items 3 and 4 both use this for each key store some value structure. So it's pretty easy to identify that we can use a map where the key is this string, the word W, or this string, the label C, and then the value is a number of posts. Again, as you iterate through your data, you may add to or update this map, depending on what you're reading in, right? These conditions here can tell us about when and how we might want to update these values in the map. But looking at this last item, we don't see this exact same relationship. Now there's two strings, the label C and the word W, but there's also this third item, which is the number of posts. How do we structure this, right? The implementation is up to you, but I'll talk about two common ways of organizing this data. The first way is to group these two strings, the label C and the word W, together in a data structure like a pair. That way, every unique pair is a key. So label Euchre with word Bauer, let's say. This is distinct from label Euchre and let's say Jack as our word in a post. These two pairs are entirely unique. This means that even though they share an element, they can still be used as keys in a map, right? Remember that a map requires that all of its keys be unique. So all that's left now that we have our unique keys, which are these pairs of labels and words, all that's left is to include the number of posts in this data structure. So that can be the value stored along any given key. The syntax for using this data structure can seem confusing, but if you use what you learned in the second part of this series, the map.h, and then you break up this larger data structure into some smaller component parts, you'll find that it's not too bad. So let's say we just found a post with label Euchre and the word Bauer, so like this example right here. We want to assign the number of posts with this label containing this word to be 1, although the syntax is pretty similar if we would just want to increment it. The number that we want to access is a value within the map, and we know that because it's the second part of our template, right? This comma here differentiates the two parts of our template. So this is one type here, and then this is another type here, and this type here is the value, right? And that value is the number of posts that satisfy this condition. So to access a value in a map, we need to get the corresponding key. So let's look at this key. This key is the first part of our template here, which is a pair of strings, right? A pair where the first is a string and the second is a string. We use the access operator or the bracket operator on our map to get the value for some given key. The key for the label Euchre and word Bauer is just a pair where the first element is the string Euchre and the second element is the string Bauer. We can construct this pair by typing out the long templated type name, right? So we would have pair and then the two types in the template representing the first and second, and then we use parentheses to construct it. But this syntax is pretty unruly, and we can just use a much easier syntax, which is the initializer list, right? So we have my map, which is what we've called this map, and we're going to index in, right? Oops, we don't want that. We're going to index in. The key here is a pair. So to construct a pair in line like this, we're going to draw this very gross curly brace. And then the first element is going to be euchre. It should probably be lowercase. And then the second element in this initializer list is Bauer. That's a slightly better brace. So this gives us this initializer list represents the key inside our map, right? It's a pair of strings. And so when you use the bracket operator on a map with some key, we get the value, right? And so here we can now assign into this value, or we can read from it, or we can update it. Here, I'll just set it to 1, right? So this is how we use a map of pairs to correspond a label C, a word W, and then the number of posts for which that have that label C and contain the word W. This is not the only way to do this, though. Another way that we can do this is a map which contains more maps within it. The key for this map is will be a string representing the different labels. So this label C, right? That's this key here. But we still have to store both the words within posts with this label and the number of posts for which we see that occurrence. And so remember that we can only have one value per key in a map. We can't have, euchre correspond to both like Bauer 1 and Jack 2, right? We can only have one value per key, unless we kind of tie all of this up together into one larger data structure. And we're actually going to create all of these word number pairs. We're going to fold them all into a map. And so the value corresponding to the key is this map, right? So let me erase this, and we'll kind of talk about how this would look like in code. So we have my map. And again, the key is going to be the first type in this template here. So that would just be the string corresponding to the label C, right? So euchre. And then this gives us the value, right? The value is another map. And so what do we want to do with this map? We want to access this integer here, the number of posts. So we're going to take this whole map, right? You can parenthesize this or leave it the way it is. And we're just going to use the bracket operator again. This time we're going to use the word W, which is this string here, right? That's how we're going to get the value by using this key. So here we're going to say Bauer. And that's going to equal 1, right? So here, instead of using a pair with 2 elements in it as our key, we're just using cascading maps, basically, and we're using this bracket operator or element access operator twice. And that basically does the same thing, right? So the choice of a map of pairs or a map of maps is kind of up to you, right? Whichever one seems the most logical to you, that will be the least confusing to you. That's the one that I'd recommend going with. Or if you can think of some other way to represent this relationship between 3 elements of data, you can go for that as well. But I'd recommend using one of these 2. So finally, we get to the main goal that we've been trying to accomplish this whole time, which is to provide a body of text from a Piazza post to our program, and then our program spits out a predicted label in return. So when classifying a post, we extract data from our trained data structures to determine the probability of any label. And when I say any label, I mean each label in our training data, or that was included in our training data. Our classifier only knows about categories that it was trained on. You can't hard code any labels in. The categories will not always be the names of the 5 EECS-280 projects. They could be the names of EECS-281 projects. They could be student versus instructor. So make sure you only add labels to your data structures when you see them in the training set. The word euchre or the string euchre should not occur anywhere in your main.cpp, only in your tests. So the spec tells us here how to find the probability that a given post X, a Piazza post X, the probability that it belongs to category C, or I should say the category of the label C. So you should calculate the probability for each label, and then again, pick the maximum of these probabilities, and that is the predicted label for this post, right? So this is like probability of C is this formula. To calculate this probability, we are going to use this summation. There's two kinds of terms here, right? This first one here, this is a log prior probability, right? So this first formula down here. And you should add this once to the probability for any label, right? Exactly once. The math is described in the spec, so I'm not going to go into too much detail, but basically you're going to take the natural log of this fraction. And this fraction is determined from the data that you trained on in the first phase, right? So here we have the number of training posts with label C. You should be able to find the number of training posts with label C pretty trivially from the information we gathered in the first part. And the number of training posts should also be determined easily. You don't necessarily have to store number of training posts as like a member variable. If you can extrapolate that from other information, like let's say you're corresponding, you have a map where each post is a key and then it has some value, right? That's another way where you can just get the number of elements in that map, right? So don't think that just because you see this information here, you need to store it as well, because you might make your program super inefficient. Just think if you can extrapolate this data as opposed to just reading it outright, right? So this, again, this ln p of c, that's the log prior probability for some label C on this post, right? So you're going to add that to the probability that this post belongs to label C. Then you're going to add all these log likelihood probabilities to the probability score prob C. The difference between each of these terms is this word here, right? W1, W2, all the way to WN. These are the unique words in the post. Because we're using the bag of words model, you shouldn't repeat calculations for words that occur multiple times in a post, right? So my recommendation is when you take this post, just cut out all the duplicate words already, and you should have basically all the unique words from the post as opposed to the post itself, if that makes sense. Again, you're going to evaluate this term as the natural log of some fraction. This fraction is derived from information you learned in the training stage. But the log likelihood is not as simple to calculate as the log prior probability. This formula here, this fraction, this can evaluate to negative infinity in some cases, specifically when a word W doesn't occur in a post with label C ever. And so this negative infinity really messes with our calculations. So we don't want to use this calculation for the log likelihood if that's the case, right? And that case is, again, when word W doesn't occur ever in a post with label C in the training data. So when this scenario occurs, you should instead use one of two other formulas, depending on how W and C relate. These formulas and when to use them are in the spec, so I'll just leave the task of transcribing that logic into math to you. But basically, just look at the spec, and that should tell you how to, or I should say, which of these formulas to use for log likelihood. And then regardless, you're going to add one of those for this term, and then one of those for this term, etc. Right? So then finally, you're going to get this, probability of some given label C. And so like I said, you're going to calculate the probability that any post belongs to each of the labels C, each of the labels you saw in training, right? So let's say you have like, prob of B, prob of D, whatever. You're probably going to have like a container as opposed to, separate variables. So you get the point. And so then you're going to take the maximum of these, right? So let's say that C is the max. Then you're going to say that label C is the prediction for this post. And then you're going to do that for every single post in your testing data set. I should also mention that the testing data set does include the actual correct label for any post. You're not going to use that label in the prediction process. You're only going to use it after you've predicted all of the posts to determine if you were correct or not, right? Basically, we're giving you an answer key, and so the classifier is going to classify all the posts and then check itself against the answer key. So that's basically used for the output of our program so that we can evaluate how accurate your classifier was. So I promise we're almost at the end of this video, right? There's only one more thing I want to talk about, which is how to use this csvstream library to extract information from CSV files. This is the documentation from the GitHub repository linked to the spec. I recommend you give it a read, but this is kind of the most relevant snippet, which shows both how to read every row of a file, of a CSV file, and every column in each of these rows. So this while loop here should look pretty familiar to you in that we have a while loop where we use the extraction operator, right, which is greater than, to store some information from a file stream into a variable using a loop, right? The fact that we use a loop means that we're going to do it for every piece of information in that file, in this case, every row. This row is a variable which maps a string to another string, right? The key in this map is the column name. So this might be something like tag or content. Those are the two most important ones for this project. And then the value is the datum, which basically means the information in this column and in this row, right? So you're going to use this row to basically access all of the information that you just read in on this iteration of the loop. Every time we read into this row variable in our while loop, the values are replaced with those from the next row in the CSV. Just like how when you read in from a text file with a string representing a word, every time you iterate over that while loop, that one variable now contains a new value because you just overwrote it, right? So row has a different value on every iteration of the while loop, but it represents the same type of data, so you can process it in the same way. So this syntax here, I want to zoom in on this syntax here with the colon is called a range-based for loop. It does the same thing as other for loops we've looked at in this class, which is to iterate over a container, going through every element, but syntactically it's a lot easier to look at. The variable which iterates over the container, which in this case is call, it starts at the first element, increments by 1 on every iteration of the for loop, and the last iteration looks at the last element in the container, right? But you may notice that we didn't, oh, sorry, let me back up a little bit. The type of call here is a pair of strings, right? We can tell it's a pair because call has an element first and an element second, right? And these are both strings. So call is a pair of string. That's the type that we get when we use this kind of iteration over a map of strings, right? We can see that map has this string-string relation, and so does this pair. But you'll notice that we don't define this pair string-string in our code here. That's because we're using this auto keyword. And the auto keyword basically makes the variable that is of that auto type to be whatever type is being extracted, right? That's kind of, I'm simplifying a lot of the both the usage and the implementation, but basically all you need to know is that you can at least use auto in this context when you're using this range-based for loop, or if the right-hand side value of some assignment is already defined, right? So you could use auto here because, sorry, that was really messy. Let's try that again. You can use auto here because column.first is already defined, right? So it takes the type from the right-hand side of the equals and puts it to the left. There's no equal inside this for loop, but it's the same concept, right? And again, the specifics of this, we're not really going to quiz you on, but we basically just want to show this to you in case this syntax is easier, right? Because once you're dealing with these maps and other large data structures, the types can get more and more confusing, nested, unruly. So the auto keyword was added to C++ to allow you to kind of not have to worry about that, right? As long as you know how to use a variable which is of type auto, then that's a lot easier a lot of the times than like writing out the full type definition. So we add this ampersand here so that this call is now an auto reference. Basically, we're not copying the data out of row. Then once we have call, we can do whatever we want with it. This example here is printing out call first with some, spacing around it, and then call second. But in our classifier, instead of printing, we'd probably want to update some internal data structures or something like that. Oops, let me zoom out. So if you're interested in learning more about machine learning, there's quite a few great courses here at UMich related to the topic. You can take EECS 445, which is the machine learning course, EECS 442, which is computer vision, or even EECS 492, which is artificial intelligence. Other than that, that's all we have for you today for Project 5. I say all we have. This is probably going to be like an hour plus long playlist. So thank you for sticking with us through watching it. We know this has been a really tough semester for a lot of students for obvious reasons. So hopefully watching these videos here has given you a little bit of insight as to what the project should look like from all levels, the binary search tree, the map, and the driver, and should hopefully save you a lot of stress down the road. Don't forget to come to office hours, especially earlier on in the project, so there's less of a queue and you can talk to an IA just like conceptually about what's going on, and use Piazza to discuss with other students kind of what this project should look like. Yeah, that's all I have for you. Good luck, stay safe, and happy coding.